Okay, Anupma, we can start now.
Okay. Good evening to all our participants. I welcome you all to IEEE Virtual Talk series, which are focused on photonics and optical technologies. So today we have with us an eminent speaker, and I would like to briefly introduce our speaker to all of you. So our speaker is Dr. Ajay Shankar, sir. He has completed his MTech in Applied Optics from IIT Delhi and PhD from Delhi University. He is currently working as associate professor and has been teaching optical engineering at Department of Physics at Guru Jambheshwar University of Science and Technology, Hisar, since 2006, and also looking as nodal officer academics under TQIC. Prior to joining Guru Jambheshwar University of Science and Technology, he held the position of Deputy Engineer Optics in Haryana State Electronics Development Corporation Limited, India. And his research interests include optical metrology, sensors, and thin films. So with this brief introduction, I welcome you, sir, for your talk. Over to you, sir. I request all the participants to kindly mute yourself. Yeah.
Interested in technological part of this. So I would like to discuss optical interferometry with you. So next slide, please. Next slide. As soon as we talk of interferometry, you all are aware that the very famous Young's double-slit experiment, which was perhaps the first evidence to establish the wave nature of light. And you know this experiment. You hope that all of you must have performed this experiment at least once in your life. And this wave nature, this result of this Young's double-slit, needless to say, but I have to repeat that this behavior of light waves as applied to our interferometry may be explained in treating the electromagnetic wave disturbance as transverse wave and sinusoidal wave, of course. The EM disturbance consists, you know, that electrical component and magnetic component who are mutually orthogonal, and it also orthogonal to the direction of propagation. Most of the interaction of EM waves with one another and with matter are dominant by the electric field. Therefore, most of the time when in particular in engineering, we are much concerned about the electrical field. So we always choose that. Next slide. Next slide. Oh, so you can, we were used from +2 levels onwards that whenever you are, see, one thing I always ask my student and always like to say that whenever there's two disturbances are there and one disturbance is falling within the domain of other disturbance, they are bound to interfere. Nothing like that, that they will not interfere. Whatever we have seen in Young's double-slit, if say that it is not perfectly monochromatic, it is not coherence or something like that, it doesn't mean that they are not interfering. Basically, what is happening that we are not able to observe the effect of that interference. So basically, you are much concerned in technically talking, this is limited by detection. So everything you know that in our life, in technology or even in science, everything is limited by detection. So this Young's double-slit observe when you are finding that you are generating two coherent sources from the same source, then you can see the fringe system. So looking at fringe system, it's okay that you are observing something, but it doesn't mean that if you're not looking any fringe pattern, two waves are not interfering. If they are two waves, and you know that in general, if one is falling in domain of other, it is going to interfere. So normally you will see these two, you will take the two waves and then contribution of one wave in domain of other wave. If there are some significant contribution, you will find that it is going to give some resultant field as such. And that field is interference field as such. And you can see that all kind of EM disturbance is completely characterized by three quantities. One is frequency or wavelength, second is amplitude, and third is phase relative to some origin. It's arbitrary. I can choose any origin till I am consistent throughout my calculation, throughout my observation. I can take any origin as such. And you can see these quantities are shown in these figures. And you know that frequency and wavelength are related to the velocity of disturbance in the media. Amplitude is a measure of the strength of the disturbance with the irradiance. Sometimes we call it intensity of the disturbance as such. All you know all these things. I'm just brushing up all these things. So you know that it's the intensity which is in case of photon or light. Let me remind you that this amplitude or phases, these are not directly measurable. It is such a high frequency phenomena. Light is such a high frequency phenomena that no detector till date, I cannot claim what will happen in future, but till date there is no detector as such which can measure it directly. So therefore, you know that light is basically a square detection type of things. Next slide, please. And then if we simple mathematically you are moving, you are taking two disturbances, E1, E2 having some phase difference delta between them, then you can easily calculate this kind of superposition. You know that all coherent superposition is always first addition in amplitude, and then you are taking its complex conjugate and multiplying both, or you can say expectation value of this. You are getting the intensity or radiation pattern as such, and then you will find that the resultant field is coming like this, and that intensity relation, the famous intensity relation is coming. I is equal to first source intensity plus intensity of second source plus twice of root under of these two intensity, and cos of that phase difference as such. Next slide, please. So you will see that these all are very fundamental equations, and you know that first two terms is the background, we call it background intensity. Even if that source is incoherent, this is always there. So you know that incoherent intensity is added in intensity itself. Slide has gone. Yeah. So you will find that usually this resultant maximum intensity or minimum intensity always depends how phase is varying, and it can be, its maximum is given by I is equal to I1 plus I2 plus 2 root under I1 I2, and minimum will be thus I1 plus I2 minus of this interference term. So this interference term is going, this is why it is called that interference term is going to modulate the result as such, resultant intensity. And this is evident from this. Next slide. And this way you will find that if it is in phase or out of phase, then either it is going to add in phase, and So either you will find that at some place intensity is going to increase, some place it is going to decrease, but overall you will find that overall the energy is conserved here. It has been redistributed. So interference pattern, interference, what it is doing, it is just redistributing the energy in a space or in time, but basically energy always remains conserved. It is not violated anywhere. So when it is adding in phase, we call it constructive interference. If it is going out of phase, we call it destructive interference as such. So you must have came across all these things in various time in your life. Next slide, please. So you will, if you will take some special cases when two intensities are usually in your classes, you might have been told that intensity of both the sources should be equal, the frequency should be same, and all these things. So in that case, you will find that famous this relation which you have derived in the Michelson Interferometer or Young's Double-Slit, you will find that I is equal to 4I0 cos square delta by 2. This relation comes, and then this relation gives all those, that maximum intensity will be 4 times of individual intensity. Then at minima it will go 0. So average will be always 2I. So nothing like that anything is violated. So when this phase is integer multiple of 2 pi, it is giving irradiance maxima, and if it is odd multiple of that, then it is giving minima. Next slide, please. So okay, so in this case, so what happens when I have so first all those slides were all very simple kind of calculation were there, but general expression, I have written here two terms here, gamma C and gamma P in interference term, and these two, one is called the degree of coherence and degree of polarization as such. So let me remind you that when I was saying that in every instances whenever there is two impulses and one is falling under the domain of other, it is bound to interfere. Whether I am observing or not does not matter. But see here, except one case, if both waves are mutually orthogonally polarized, if polarization is orthogonal to each other, then there cannot be any interference. But this is again an ideal case, that exactly saying that gamma P should be 0, again it's ideal case. There is always some kind of misalignment and all these things. So some kind of contribution can be there. But in technology, we always believe that if that change is not measurable, if it is beyond the capacity of any detector as such, it is not detectable, then I can safely take 0. So in that case, as soon as it is going in the limit of non-detectable, then we can say that it's 0, gamma P0. Similarly, when slide has changed, this was an earlier slide. One is maximum, and if I1 is equal to I2 is equal to I0, then it has to be 0. So this case I have already discussed. Next slide, so 9th number. So this point, I1 plus I2, I have added two terms, gamma C and gamma P here. One is polarization term, gamma P, and one is coherence term. So both, they are perfectly coherent to each other. Interfering waves are perfectly coherent because we take it 1. If it is perfectly incoherent, it is 0. You know that nothing is perfectly coherent or perfectly incoherent. So there will be some value between 0 and 1. Similarly, gamma p, if it is perfectly orthogonally polarized, one polarization in one that plane and other 90 degrees to it, then it will be always 0. So if it is some significant value, then it will be there. So we must take care of all these two terms also. And you know that in all these equipments and all these phenomena, this phase basically comes from the what is the path difference between two waves arriving at the measurement point, and this optical path difference, it's a very important parameter for all kind of measurement as such in our life. So most of the time I know that this optical path phase is related with the 2 pi phase is equal to lambda 1 wavelength difference. So you can correlate that both. Next slide, please. So basically, if we were taking any two sources as such from where usually that because we have put here a condition that it should be fairly good degree of correlation between two waves, means they should be fairly coherent. So that case you always know that you are so usually we are generating all 2 or 3 or multi waves from the same source to figure out and to meet out this requirement. But this phase difference can be either generated due to, you know that optical path length is always multiplication of refractive index of the media multiplied by the physical length. Therefore, either that physical length is changing or refractive index is changing. In both cases, you will find some kind of optical path difference generated, and accordingly you will find that 2 pi by lambda multiplied with that OPD will give resultant phase difference. So this, the first case was when two media is changing, both arm having the same length, still there is a phase difference between two waves. In second case, media is same and path is changing, then again some phase difference is coming. Therefore, you will find some changes in pattern as such. Next slide, please. So coming to the what I was talking about, the interference, basically science of interference or interferometry closes there. Now, what I told you that whatever it's all interference is taking place, but how to observe that? The effect of interference, how to observe that, and for that instrument we call it that optical interferometer, a versatile instrument has been developed so far, and this is this kind of maybe most popular kind of interferometer, maybe knowing that Michelson Interferometer and use that every places in laboratory, science or engineering, everywhere you can say that this is one of the most not in optics, but all over in any kind of field, one of the most utilized instruments so far on Earth. This is optical interferometers, and this is used for precise measurement of beam of light, such factors of length, surface regularity, and index of refraction. So, and we have seen back that you need minimum two waves. If it is, you know that even 3, 4, 5 or n number of waves will also be interfering, and you will get the different kind of interference pattern. But minimum two waves is required. So it divides a beam of light into number of beams that travel unequal path, and also beams that travel unequal paths, and then they superimpose in the observation plane, and that results in some kind of interference signal, and popularly it is known to be interference fringes. Next slide, please. And you know all these are our most interesting things with, on which we, the engineers particularly, and those scientists even who are interested in instrumentation part of interferometry, you know that you are in laboratory, you were first, hopefully in all those students have first used this Michelson interferometer to measure the wavelength of light as such. And then you know that the best commercial application, or you can say that most utilized commercial application of this in Michelson interferometer is laser interferometer to measure displacement. So very small, right from very small displacement to, with the advent of laser, they can measure even meters and meters of displacement with very precise measurement. And you know the beauty that even I can see visually shift of one fringe pattern. And you know that one fringe pattern shift when path difference changes in Michelson interferometer by lambda by 2. So lambda by 2 path difference, if one mirror is changing, moving relative to other mirror lambda by 2, means you can see one fringe shift. So any layman can measure that one fringe has shifted, means half of the wavelength. And if I am using 0.5 micron wavelength light, it means by just counting the fringe, you can resolve half of that. So 0.25 micron just by counting. And just beauty of this device is that this one fringe change have 2 pi phase difference. And you know 2 pi phase difference is 360 degree. 2 pi means 360 degree phase. And you may be aware, you might have heard about the LIGO and all these things, that the big instruments that interferometer. Now people are able to measure 1 degree, less than 1 degree of phases. So if I can measure 1 degree phase change, means lambda by 2 divided by 360. So nanometer. So very easily you can just by just a inspiration comes, or people are doing in India. We are not able to do all these things. It's a different kind of story. Some it's a never-ending story as such. But maybe knowing that even though Arizona people and a lot of people, they are even measuring some fraction of this degree of phases, and they have gone far ahead in nanometer range. And nanometry, nano technology depends on that. If you can't measure nanometer, what else this nano guys will do? So therefore, the existence of nanoscience depends on this nano measurement as such. So, and then again, you know that this particularly n wavelength or multiple wave interferometer, popularly may recall that Fabry-Perot interferometer, that is very well used in the study of spectral lines, fine spectral line. Then refractive index, practically we are measuring, we are doing all kind of astronomical work and all these things with the interferometer. Next slide, please. So basically our architect of any interferometer goes like this, that we need one coherent source. You are splitting, that typical quiz comes that can you generate, can you take 2 helium neon laser and still you can get some fringes? And you always say no, because they are 2 different helium neon lasers, they are not perfectly correlated. Therefore, you do not see any fringes, although interference can take place. So usually you are splitting 2 beams or multiple beams from the same source. Then by some means you are recombining in 1 beam which is not being disturbed, we call it reference beam, and second beam where you can put some measurements as such, And that is target beam, where you can disturb the phases, and then both these combines, and then you are finding that there's some kind of interference field is generated. And if I have some detector to detect this changes, then you can measure all these parameters which is going to affect this field as such. Next slide. And next slide, what I was talking about, this most versatile and most popular interferometer, we call it the Michelson Interferometer. And this again, the same that last block diagram has been realized here, that you are using this this way, that a monochromatic source is being split by a beam splitter. Either it can be a plate kind of beam splitter, or a cube kind of beam splitter, or pellicle kind. You might have been all guys who are interested, or you are doing some kind of optics, you know there are huge design constraints and design challenges for this beam splitter itself, and a big huge market, right? This beam splitter, and this is splitting these in two beams. One is going in fixed mirror, other is going to movable mirror. Then it's coming back, and then it is being going to the some phase measurement electronics. And this cyclic, of course, it is because they are interfering, it will create some kind of fringes. So this electronics will see a cyclic intensity change in the interference pattern, and whenever any kind of phase change is coming either of the beam, it will be changing that pattern, and accordingly signal will be changing. If you can measure that signal, that you can do the all those back calculation, what kind of change has seen. Next slide. So these are the few calculations where it is how it is correlated with the source wavelength and refractive indexes and phase changes and all these things. So it is related with these two equations. You all know, I hope. Next slide. Next slide, please. So all this is that just the some additional terms I have taken, how to correlate with the vacuum wavelength and all these things. Change it. Next slide. This is earlier that equation. I can have either you have to take some parameter here, whether it is say like in Michelson interferometer, light will be, if some path length is changing, it is going once upward and then coming back, so it is traveling the error twice. So a factor of 2 is coming here. If it is going 3 times or 4 times, accordingly we have to incorporate all those factors. So phase change in either reference or measurement beam is taken care here. So change it. Next slide. And so then you can take care of all these, whether it is changing in wavelength, length or index. So you will just express like this. So change in both will be taken care like this. So you will differentiate it, and you will find that ultimate whatever change has been taken place in the measuring mirror or target mirror will be given by this equation. Change it. So till now, I was always talking at whatever you have learned that both beams should have same frequency, means same wavelength. You might have noticed earlier that I write one term homodyne. So in commercial world, we call it, whenever I am talking about that two wavelengths should be, both sources had been same frequency or wavelength, then that kind of interference or that kind of interferometry is called homodyne, because frequency are same. But I hinted that whether frequency is same or little bit different, interference is going to take place. Or you might recall one thing, that if two different frequencies are interfering, you may recall in sound wave that bit frequency. So here also, if I have two very closely differing, very small difference between two wavelength, like G-man laser, helium laser G-man splitting gives two very closely spaced modes, or you can say two different wavelength of helium laser having two close frequency as such. And that has been in massive way, or you can say very effectively used in interferometry. And this kind of sources, where I'm using a source which has two frequencies, they have been used, and in that case, you will generate a bit frequency. And you can see that if those frequencies very closer to each other, then this bit frequency may be to such extent that this frequency, that frequency can be taken care by a photo detector now. And this technology has been very effectively used by commercial people to use this heterodyne or dual frequency interferometers. So all those slides we were talking about, that single frequency, these are the class of homodyne interferometer. But there is second class also, which is called heterodyne, where two frequencies also can be used. Next slide, please. So in homodyne case, provision of power normalization to the mitigate sensitivity to the spurious intensity, and you know this all these quadrature signal processing, quadrature output of provision of. If I am measuring anything, you know that to take care of movement as well as direction of movement, you need that quadrature signal, and this some noise suppression devices, because you know this I1 plus I2, that first term, which I was calling that average intensity term, this sometimes called DC term, and that interference term is called AC term. That DC terms is always a very bad thing. It's a noise kind of things in the instrumentation. So that has to be, that is not a very acceptable thing and good thing. So next slide. So usually a homodyne interferometer system is made of a laser source, polarization optics, photodetectors, and measurement electronics. Depending on the features they usually requires from the homodyne system, direction sensing or power normalization, a lot of very tricky kind of electronics, or you can say signal processing, are required. And homodyne source is typically a helium source, that nowadays even laser diode is very effectively used. And usually they have two beam consisting of two opposing circularly polarized component. There is that polarization is also used effectively, and to in order to observe the interference, the two beam must have same polarization. So you have to manipulate even polarization and all these things. And this is used with the using some kind of polarization optics, and ultimately enforcing, you have to ensure that whenever in the observation field where it is going to superpose, you must realign the polarization there. Next slide. And this I have taken from the most of this slide I have taken to those commercial equipment manufacturers, and you can see that they are taking all care of all these things with such a very delicate kind of optics. This kind of the mirror kind of things you are saying, that that prism, that is retro reflector. I hope most of you is maybe knowing, and such a just drawing and talking about retro reflectors is a very easy kind of things. But realizing these kind of things requires a lot of special specialization, not only in fabrication, but its measurement and metrology itself. And here also this maintenance of angle and everything, and errors in retro reflector, all these components. It's only the interferometry which can solve this. Because if you know that if any kind of error is introduced here itself, you cannot measure better than that anything. So you have to fall down on the interferometry itself. Next slide, please. And then the heterodyne. Next, change it also. So in heterodyne, two frequency, or sometimes it is called AC kind of interferometer. And time is perhaps 40 minutes. Okay, so change it. Next slide. Why I'm taking these slides? Because it may inspire some of you that how this polarization, when you will go at the website of Zygo or Vico or even Renisa, you will see that how beautifully they have exploited this concept of polarization and all these things to the detection of this hit frequency of and change due to changes in signal due to this bit frequency in heterodyne interferometer. So this is a very interesting device as such, heterodyne interferometer system. Actually, homodyne interferometry system detection is not tricky compared to heterodyne. So system is very, next slide. So you will see that in heterodyne, even laser is very costly. So dual frequency laser is costly. System becomes a bit tricky. Next slide. So this kind of system is used there. Now time is so move again. Next slide. Oh, so this is the heterodyne system. This kind of change kind of calculation will be coming, and this kind of bit frequency and all these things. Sometimes it will be called Doppler shift and all these things. So these are the scientific terms. You can say bit frequency or Doppler kind of change, acceptable to all of us. Next slide. So these will be some kind of mathematical changes. So these are the constant phase intensity changes at this kind of signal. Next slide. So it will be coming. So basically, you know that your aim is to change all these things. Next slide, change it. So you will, let me say that heterodyne, talking about heterodyne is a very simple way, but it needs a very highly stabilized two frequency helium laser, and it's a very costly kind. So this two frequency laser is a costly device, and it has what I just told you, that it consists of its hardware cost is a little bit higher compared to homodyne, although electronics will be costing less. Change it. So this is a small kind of simulation. You can see that how measurement signal is changing and how this. This is ZMI, Zygo, measuring interferometer as such. And then next slide. Of going after this, these are all that homodyne, heterodyne, mostly this displacement measuring interferometry. Then this is just I remarked that whenever you are measuring any component for this interferometer, ultimately we have to provide the interferometric setup to test the component itself. And you all have used that Newton setup, Newton rings in your BSc or MSc classes, and that now you can recall that the fringe pattern observed in the Newton's ring was basically giving the profile of the surface of that lens as such. One component was plain reference flat, and another component was at top of that was that one curved surface, a spherical surface. So now we can correlate that rings, that circular fringes, that was giving phase profile of that lens surface as such, and that is being the very basic interferometer you might have seen your CSIO in every lab. Everywhere we are looking at this piezo kind of, or somewhere we are also calling Newton setup there. And you can see this is a very small kind of setup where reference flat and test flat you can use, and you can see what kind of mismatch between two is there, and you can see some kind of fringes. Change it. Next slide. So you will see that if the difference between one wavefront coming from the reference surface, other is coming from the test surface, both are superposing, and it is giving some kind of interference field and a typical interference field. You can see if both are perfectly flat, you are giving some kind of tilt, you will see this kind of a straight line fringes. And hope students working at CSIO, I hope that all have seen this kind of fringes. At least I hope this. And next slide. And then you see that this now the most of the piezo interferometer available for the test equipment as a test equipment in the commercial companies. We call it piezo interferometer, laser based or laser interferometer for testing the optics. This has this kind of configuration. You have one source, either take this side or that side, and you will, because you know that if you are using piezo kind of setup, you might recall that if you are using a sodium lamp, you have to keep both those surfaces in contact to each other due to problem of a minimum that coherence length and all these things. But once you are using a laser, you have a leverage to increase this length, because if you are putting in contact, then a reference surface can be spoiled by the test one, and that is an undesirable one. Therefore, we are constant, we are encouraged to use laser source, and that you know that laser has sufficient coherence length, and here you can if you even if you are giving a lot of gap between reference and test surface, still you can see the fringes, and that is exploited here. Next slide. And then you are encouraged to see all these things. Whatever you have learned in optics, or that spherical aberration, this aberration, that aberration, you can see all these things in laser interferometry. If you use any kind of thing, you will see that defocusing or any kind of aberration. See, this is a spherical aberration. If some kind of if tilt was there, I just tilted the two surface, that fringe was straight. If there is some kind of spherical aberration, you can see fringes will be something like this. So next slide. So you can see all these if some kind, you can even, there are certain kind of software freely available for all these things. DFT Fringe was one software. You can use you can download that and just simulate all these fringes. It's free there. So you can see all these things. There is some kind of aberration you are putting in one wavefront, what kind of resultant interference pattern you are going to see. Next slide. So comma will be another thing. Next slide. And when I'm coming towards end to this topic, I'd like to introduce what one topic which always fascinate me. The nowadays the very dominant field of interferometry, we call it phase shifting interferometry. You might have seen that all these kind of the fringe analysis I was talking about, they are all some kind of a static kind of phase measurement. But as soon as this was developed by Professor Buoyant group in Arizona, and after that it has taken the central stage everywhere. This phase shifting interferometry has given a direct clue to measure that what I just remarked earlier, that even less than 1 degree phase changes. So this is a measurement technique which always fascinate all people who are working in field of interferometry as such. And you can say, I always claim this is a single biggest event in last 30 to 40 years, the development in phase shifting interferometry. Next slide, please. So this the basic of this you can find in any book as such, but you will see that those basically if you have one test wavefront, other is reference wavefront, the wavefront will have some kind of expression like this. You can do all these things, and of course when it will be superimposing this kind of one AC component. Now I am giving in this I1 plus I2 as a AC component part, and that interference for that interference expression, one is that AC component or modulation component multiplied by the phase cos of that phase, and all the one is called the average intensity. Also, so this is the simple things. I just rearrange the things, nothing like whatever I've shown in 2 slides earlier. This is so change it. So this is the basic equation for the fundamental equation which they have used in the PSI. And next slide. So what we can see that if I can generate 3 or 4, because see I have now 3 unknown. One is this amplitude. You can see that this DC component, one is that modulation component, and one is phase component. So 3 unknown is there. So if I can generate 3 interferogram with the known phase changes, then I have 3 equations there. So now I can generate some kind of, I can manipulate these 3 equations. I can generate the equation for relation for the phase, and this has been done here. I have taken only the 4 frames. So frame 90 degree phase shift, 0, 90, 180 and 270. So pi by 2 apart, 4 interferogram, and then you will see that tan phi, that phase term, you can directly, if I have such 4 kind of phase shifted interferogram, that will give me instantaneous value of phase at that point or time, both. It can be temporal, it can be spatial. So very big achievement as such, very big technical concept. And you know that Professor Buoyant is a very big name is in industrial field as such. So that has been used. And next slide. And the way they generated those fields by using this kind of arrangement by bay plates and all these things. So some fluorescent beam splitter and everything, they could generate 4 different interferogram, and that has been used here. And if I can, next slide, and by that they could measure this kind of beautifully they can generate that. Next slide. They can measure these phases, and next slide. So next that of course this that as you are seeing, you can see that that phase equation was tan phi or tan of that phase. So of course it's not moving. So it will be a wrapped phase. I'm not able to change the. Oh, okay. So this way you will see that the left hand side you can see this kind of this fringe pattern, but actually this is a wrapped phase. The pattern that diagram that is shown in right hand side, and this wrapped phase that there is now huge number of algorithm and all these things to unwrap this phase. Next slide. So that has been wrapped, and you can see the profile actually what is the profile of that surface. So this way they have you can measure. Next slide. They have measured the surface profile. So I have taken for easy showing that a spherical surface will be shown like this. But even if it is any kind of, so you can see this, the profile of this phase profile will be indicative of surface profile itself. So it gives the measurement as such. Next slide.
Yeah.
And so these were all kind of temporal phase shifting as such. And when you will, next slide. So when you will be at another very fascinating kind of now with the advent of CCD. CCD, you know, this pixelated CCD, this has given another kind of phase manipulation kind of things where if you can somehow you can generate this detector bit compensated. If I can generate a kind of fringe system and I have a detector whose 4 pixel is matching to 1 fringe width, then you can see that first pixel will give the information about 0 phase, second will be giving pi by 2 phase, third will be giving 180-degree phase, and fourth will be giving 370-degree phase apart. So all 4 phase those interferogram that 4 equation which we were trying earlier, you can see that this is encoded here. And nowadays, with the advent of this CCD and rather fast CCD now, these are being exploited by that. Next slide. So by using this charge coupled devices and CMOS devices, this 4 quadrature signal even you can generate from the same frame now. So these are all some interesting things there. Next slide. And then one more thing, perhaps you people at CSIO Chandigarh, you can solve this problem to the Ambala industry or industry around you. You maybe you must have you or either in your life you will find some request from the industry. Can I do if one interferogram have all those information about phases? Why I cannot get all this information from same interferogram? And when you will see your literature and industry strength now, and you may recall Professor Takeda from Japan, he really did this. He used the Fourier transformation concept to get that information. Information. So Takeda showed that using Fourier interferometer, Fourier transformation, you can get all these information. So to me, it's a very good concept if somebody tries to solve this kind of problem for our local industry. Your Chandigarh industry in and around, they are badly looking this kind of solution there. So you can try this kind of solution. The next slide, let's run through remaining 3-4 slides. So you can do all these things. Then your mask making, they have given you this kind of provision that even in same interferogram you can generate 4 phase shifted interferogram by using phase shifted masks. All these things. Next slide. So this kind of these are some variation of temporal phase shifting and spatial phase shifting as such. And this way they have. Next slide. They are using this this kind of very successfully. They have been used, and so perhaps at the end of this presentation, and so next slide, last slide, perhaps by holography. They have used this, and lastly, I have complemented these 3 firms: Zygo, Vico, and Renisha. They are my major resources. Whenever I am looking for any kind of inspiration, I always look at these 3 companies. They have done a huge technological advancement in interferometry, whether it's a profilometry or whether it's a displacement interferometry. So all these things. So this is all from my side. Thanks for listening.
Yeah, thank you so much, sir, for a very fruitful session. So, I firstly request all the participants to kindly mute yourself. There is some noise coming from the background.
Yeah. Oh, they can.
Yeah, Dr. Hemant. Dr. Hemant, kindly mute yourself. Yeah. So, sir, if you look into the chat box window, so we have 3 questions in the chat box.
Yeah.
So, taking the first question from Rohit Hazra, he's asking what type of interferometry systems are used in LIGO? Yeah.
LIGO is basically a Michelson interferometer. This is a very large arm length as such, but LIGO is Michelson itself.
Okay. So Rohit, if it's not clear, you can directly interact with sir. You can unmute yourself and you can talk to sir. Yeah. If you need more clarification on this.
The LIGO, they have a lot of huge resources available, and LIGO is where you can learn a lot of interferometry. Even in this phase measurement, all those advancement came due to LIGO.
Okay, sir. So, sir, going to our next question from Sandeep. He is asking, is DFT fringe software? Like, if this software can do fringe analysis from interferogram.
Yeah, it can.
DFT
It can.
fringe software.
DFT fringe can do, but and beauty is that its source code is available. Source code is in C. So if somebody is conversant with the C language, you have command in C language, please collaborate amongst each of you. If if one guy is trying to do something, it's almost impossible. Now interferometry field is such an advanced field now that you will bound to discourage as such. I will not say fail, because if you will try for 3, 4, 5 years, you are bound to you will be successful. See, I always believe that there is 3, 4 year gestation time. So you have patience to work for 3 years. I always take 3 years. If you have 3 years gestation time, always go for that. But the kind of problem, the kind of advancement is going on, I request you to collaborate amongst you. You need one person who is very versatile in C language. And DFT friends do have code in C, so you have to control that. Whether you can't go for MATLAB. MATLAB will not be a commercial success. Either you will do in Python or C. So you have to either a Python expert or C expert. So try that.
Okay, sir. Thank you. So going to our next question from Abhiram, sir. He's asking, are masks used in photolithography?
Masks.
Yeah, mask.
Photolithography mask is an integral part as such. And mask I have intentionally left one very critical component of or field of interferometry, that grating interferometer. And grating interferometer, that phase grating is always made using mask for this thing. So mask is part of that.
Okay, sir. So going to our next question from Niranjan. He's asking, what is the basic difference between interferometry and photometry in any spectrophotometer?
Photometry is nothing to do with interferometry. There two beams are neither, you know, that there is nothing like requirement of coherence and all these things. They are that is essentially a incoherent phenomena as such. There you are doing everything with the intensity of the beam, not concerned with the amplitude and phase as such. So photometry is a different again as such. There you are this is a incoherent phenomena, and interferometry is essentially a coherent phenomena. So different kind of things. To there two beam, both have difference and target is there, but they are not coherent. They are incoherent.
Okay, sir. So going to our next question, can we check the thin film thickness layer using interferometry?
Yeah, very well. It's a very big tool. It's a very big tool as such, interferometry.
And he's asking, if yes, then which interferometer is used?
See, in thin film, you can go through there is a number of companies, they are offering commercial interferometer also, and they are using even some kind of normally, because when you are going for thin film measurement, usually you may be talking about inline. So when you are using inline, then you have to take one reference probe, and that probe will be going either inside the chamber or you are either using outside. So it cannot be common path. It must have two different paths. So usually there also this Michelson is very successful as such.
Okay, sir. So next question is from Webber. He's asking, is there any contribution of interferometer instrument in finding or analyzing black hole?
Not known to me. I'm not. I've never ran after this kind of a Big Bang black hole. So I'm at ground level. So I've never seen that.
Sir. So next question is from Preeta. She's asking, like, can we measure change in refractive index by interferometer?
Yeah. This is. I've already mentioned earlier that if you are taking the both arms equal length, and whatever changes refractive index is changing in another arm, that is going to be the ND. I mentioned that OPD is refractive index times the physical length. So either change in physical length or index. If that is going to change a phase of 2 pi, one fringe is going to shift, or 360 degree phase is going to change. So even that, and it's a, I remember perhaps CSIO already done all these things. It has been done when I was around Ambala, that people were doing this. So please see your CSIO archives. You will find its solution that they have used. Or remember that analysis of gases and all these things, where you are taking measuring changes in refractive index and all these things. You are putting one tube in the measuring arm, and their refractive index is going to change when some concentration or density is changing in the gas. Index is changing, and that is going to give you phase changes. So already done a lot of work there.
Okay, sir. Thank you. So that's all from the
No.
questions from the chat box. So now the session is open for direct interactions. So if anyone want to directly interact with sir, can unmute yourself.
I
and-
wanted to know from the speaker that how does this is interferometer can help this laser communication in the field of communication area.
Communication area, see, again, it's a rather I have never, because it's none of my fields, I have never tried that, but I don't think that if you are going to use that some kind of modulation and demod or mod kind of things, and there phase you are going to use phase or that kind of things, there it may be some use, but I have never tried to put up my mind how it is going to help in communication. Of course, communication component, they are being all standardized and everything, all those, even that your fiber, you can say that all kind of measurement, that fiber interferometer and all these things, their interferometer is coming in. Now fiber is already a part of fiber interferometers. They are very popular kind of things, is sensors now, but I have never came across any this kind of requirement that what can do in communication directly as such. So I'm not aware of that.
Okay, thank you, sir.
Oh.
Okay, next.
Shall I ask one question?
Yeah.
Yes, ma'am.
Why not?
Yeah, actually, interferometer we are using as a biosensor by using
Yeah.
like our simulation tool. So my question is, their beam combiner and beam splitter will be there, because when we are talking about interferometer, one will be reference arm and one will be which arm where we'll put our bioanalytes. So experimentally, I never did experiment. So I want to know whether interferometer will come in physically, like experimental hardware, along with the beam combiner and beam splitter.
Yeah, it is coming, and it will, now you have a lot of option. I have seen that biosensor and bio people, they are using most of the time this fiber kind of interferometer also. That that fiber 3 dB coupler, it is beam splitter and combiner itself. It can split and combine the beam. So even all those things, I have came across a number of cases where they are using this kind of fiber coupler and all these things to doing. But whatever, once you are ordering for interferometer, they will essentially, it will have one source, beam splitter, combiner and detector, everything. They have to. You need not to place anything, any order for things
Separate.
separately. Yeah. It has to be. Interferometer means a source, splitter, combiner, detector, and even nowadays processing software. So if you are buying all these things, be careful that bargain from any supplier. You have to demonstrate your outcome. Never say that I need your this component. Your first, from my industrial, what we do in industry, we always call the seller and we say that this is my problem. If your equipment can demonstrate that you will solve my problem, then I will buy. Otherwise, no. So what will happen? Even they have some kind of problem, that supplier is bound to demonstrate that interferometer is working. So my suggestion will be that go, or even in R&D, go in the industrial way. Bargain for the outcome, that I will pay 10% extra, but you have to ultimately demonstrate your interferometer is working for me. That's all.
Okay, sir. Thank you, sir.
So anyone left?
Yeah, anyone else?
So it seems over. So
Yeah. So if anyone is there and want to interact, so this is the platform you can. Before we end up today's session,
Anupma, I have one question.
yeah, Nagendra Prasad sir. Yes.
Uh, Ma'am, I wanted to ask the speaker that um, uh, can we have an interferometer with the two arms in two different mediums, or should we have that in same medium?
no. You can put in any media. Both can have different media. If
Sir, because
only
one
thing
is
is
of
that, you see, one is the if you are one is unknown, then it will be very difficult for you to know the result of both. So ultimately, you will be getting some kind of you can develop some kind of algorithm that can even both are unknown, and if you are taking a huge large number of frames, large number of interferogram. See, what I have said, that algorithm, they are showing that as many unknown, you need that many results.
yes.
So once you have, you just set up your own equations and see that now have this is unknown, this is unknown. So how many results interferogram actually I need, and then like you can intentionally put some unknown change in one of that arm and see the change what is happening effectively in the interferogram, and that way you can calibrate it. So and then you can find out those. It's perfectly fine. People are doing these kind of complex things are there. So and what is there that it's not always necessary that I should have only two arms. Even three arms interferometer is possible. These are possible as such. So nothing like that. Only thing is that nowadays tool is very fond of computation and all these things. So it's not like early time that you are stuck off that how to solve it. So this is a very good problem as such, that if both are changing, then what to do? You will need some kind of trick. So whatever electronics guy says that you give some known parameter and then calibrate how it is changing and do all these things. So it can be.
Thank you, sir. Thank you, sir. This was a
Oh,
very informative lecture. Thank you.
thanks.
Yes. Hello, am I audible?
Yeah.
Yeah.
Yes.
Sir, so my question is like, does this interferometry also has its application in space domain? And like if it is, then how it is used in space telescopes?
A space telescope, they are, you know that all these that I might have shown one application part in last. It was last point application part in space itself. So it has been very big field, or not even optical invisible or all these things. Even you radio interferometry they are doing. So all this whenever there is very small change taking place, and that small change, that is encoded in phase information. Any small change in any electromagnetic signal, you cannot directly measure its amplitude and phase. I have told you very early that here we are using square detector as such. Detection process is square. You cannot a straight wave like in sound or any other wave. You cannot measure amplitude and phase. So ultimately, this what is the irradiance, though square of the amplitude. And so, if any minute, any kind of change which is encoded, that will be encoded any very fine happening in even a space, that is encoded in phase. And those radio telescope and all these things, that radio interferometer, they are all taking care of that. So because that phase information, they are targeting measuring the phase. And so very well, it's a very effective, or you can say, perhaps before this Michelson, this direct phase measurement, PSI, or displacement measurement, this space people are using this interferometry.
Yeah. Sir, we have one last question from the chat box. So he's a person is asking, in a LIGO experiment, one can measure change in path difference at an order of 10,000 times smaller than the proton. So he's asking, what makes it so sensitive? Is it the lengthy arms and precision engineering in LIGO experiment?
Yeah. Very true. It's some kilometer length. So they have increased the sensitivity by increasing the length of both arms. And then what I told you, that this PSI, the phase measurement, when you will see their literature and improvement there, the way I was talking, that fraction of degree. So they have gone in seconds as such. Even phase change of seconds, they have measured there. So this is a very big project to develop a phase measuring algorithm there. So
okay, sir. Thank you so much. So any more question from the participants? Last call for direct interaction with sir.
you can share my email and mobile also. They can interact anytime.
Okay, so I'll share your email with the participants. So before we end up this session, I thank you, sir, for a very informative talk. Our participants really enjoyed and they learned a lot. So before we end up, I would like to request you to kindly turn on your video. We can have a group picture. Yeah, if it's possible. I request the same to all the participants. If they can turn on their videos. Yes. Yeah, so I'm waiting for the participants. Yes, we are waiting. Another 1 minute, quick. Hello, mister.